Okay, so we saw what counting measure was, but if you have any measure for that matter, the way to do integration is first to do for simple functions and then approximate whichever can be approximated by simple functions. You can push the meaning of the integral for that. There are various ways of looking at it. I saw first started with Riemann and saw how we approximated, and the step functions were approximated by simple functions, and we went through that. There are various other ways of looking at this approximation. First of all, the idea again is as follows. Okay. So, let mu be any measure for that matter, not necessarily counting measure. Suppose you have a function f, well, you have to have some property of the function f, and it is called measurable function. Okay. Let me put this again. I am doing a course, 2-day course on measure theory and integration, but it does not matter. Okay. Suppose I have a function omega to c. Okay. Well, think of this as the sample space, and this as a complex valued random variable. Okay. If you are familiar with that language, it is a complex valued random variable. Omega is the sample space with each point in omega. If you put r here, you get a real valued random variable, which you are all familiar with. Okay. Most of you are familiar with. Now, suppose I have a function from omega to c, then I want to define the integral over omega of f with respect to the measure mu. So, mu is a measure on omega. Okay. So, this is what we saw last time. Now, I am going to look at it in other ways also, just to understand what is going on. Okay. So, I have a set omega, I have a measure on that set. If you have the total measure is 1, it becomes a probability measure, but in general you can have even infinite measures. The total measure could be infinite, like the Lebesgue measure of the real line, the total length is infinite. So, we can have either a finite measure or an infinite measure. If the finite measure is equal to 1, it is a probability measure. So, as I always tease my probability friends, you always do only analysis where mu of omega equal to 1, that is all. Okay. But there is much more in probability than that. It is only just to pull the legs. Okay. We want to define this. Okay. As I pointed out last time, the first step is the so called simple functions. What are simple functions? Suppose now k1, k2, kn are subsets of omega for which the measure is defined. So, they are called measurable sets. Okay. The mu of k are ones are, so they are called measurable sets. Measurable sets, that is, they are events. Okay. In the language of probability theories, they are events. Okay. They are measurable sets, that is mu kj is defined. So, I have a finite number of measurable sets. This is the one that is copying intervals. Okay. It is the generalization of the intervals on the real line. For every interval, we have the length, which is the measure. Instead of interval on the real line, replace the real line by a general set omega and the interval concept by a general quantification called measure. So, I have a measurable sets, finite number of them, k1, k2, kn, and without loss of generality. These are technical details which will not bother, that kr intersection ks is empty, that is, they are disjoint measurable sets. So, here is omega, and I have k1, k2 and kn. So, I have n measurable sets which are disjoint. Now, what we are going to say is suppose I have, so let A1, A2, An be positive, let us say positive or even non-negative. Better to have positive, well, okay, let me put non-negative, be non-negative real numbers. Okay. And then I am going to say you throw a ball from here, if the ball falls in K1, the payoff is A1, you know it is positive payoff, and if the ball falls in A2, K2, the payoff is A2. It is like K1, K2, Kn are banks. You invest money in these banks. If you invest in K1, you get A1% interest. If you get invest in K2 bank, you get A2% interest, and so on and so forth. So we have now these positive, non-negative. Of course, the bank cannot say, I will give you have to give me interest. So the Swiss bank does that, but we don't do that. Okay. So that will come to handle Swiss banks also later. Anyway, non-negative real numbers, and I have so f a function from omega to r, okay, omega to c, such that f of omega is aj if omega belongs to kj, 0 otherwise. Okay. It takes the value aj on the set kj. We can write the technical way of writing this function is f is summation j equal to 1 to n aj, the characteristic function of kj. Characteristic function is the one which takes the value 1 on that set, 0 outside, and that's we can write it in that form. Such a function will be called, such a function is called a non-negative measurable simple function. Will this improve? Huh? Uh-oh. Can you see the board? Anyway, this is not functional analysis, since I am going to only review integration. You can have a look at it, and unfortunately this will not be recorded, but we will have the notes. Huh? Recording. Oh, then it's all right. So you can go through the recording later. Yeah, if this light comes, I will stay with the board where. Oh, that's better. Can you now see the board? Yeah. Okay, such a function is called, is the recording going on? Is called a non-negative. This word non-negative because the values are all non-negative. We take 0 or positive values. Simple function. This is just the generalization of the step function of Riemann. Step functions take constant values on intervals and the remaining places 0. A simple function takes constant values on measurable set, finite number, and 0 elsewhere. So suppose I have such a function. Following Riemann, we define integral f d mu or omega to be simply aj, the measure of kj. The integral of such functions is simply this bank gave me aj rupees, this bank gave me a1 rupee, this bank gave me a2 rupees, this bank gave me an rupees. The total income is the integral. That's all. Okay, that is the total income I got from my investments. This is the simplest thing, generalization of the integral over an interval. If a function is constant over an interval, 0 elsewhere, it is just the area. Okay, the base into the height, which is the value. That is the generalization. These are all generalized rectangle area formulas. Okay, right. So now we have this. Then what we do is we can go through all the other things that we did. but there is one thing that we can do is the following. I will not go through the details, but I will tell you what is happening. Now suppose I have a general function f omega to r, omega to c, general real valued function. The values of the function are real. I have a real valued function on omega. We say it is measurable, f is measurable, mu measurable, but it is measurable. Okay. If the set of all, okay, what should I say? Let me take real value. Okay, so first take real values. Okay, let's take real value. If the set for any x, the set of all in R, the set of all omega, such that fx is less than or equal to f omega is less than or equal to x. Remember, this is how you get the probability, cumulative density function and all that. This set is measurable. Measure of this set is defined. Okay. For any x, the measure of this set is defined. In probability, we call the probability of this as the cumulative density function fx. Okay. That is exactly what we do there. Okay. So this is only a technical requirement for something that will to make something work. Okay. Now take a general real valued function such that f is greater than or equal to 0. It is non-negative. The technical fx is greater than or equal to 0 almost everywhere. All the technical you leave. Just look at intuitively what is happening. F is greater than or equal to 0. The moment you have such a function, it can be approximated by such functions. What does that mean? You can get a sequence of simple functions which converge to f in a very systematic manner. Starting from the bottom, they slowly improve and go up to f. For such a function, for such functions, we can get a sequence fn of simple functions, non-negative simple functions, such that fn of x increases to L, non-decreasing. It may be sometimes constant and go up. This is non-decreasing and converges to fx. So from below we slowly approximate the function f of x. Now we know how to define the integrals for this. That was step 1. In step 1 we define the integral of non-negative simple functions. So by step 1 we can define integral mu fn d mu. This, let me call it step 2. Okay. Step 1 was non-negative. So I can now define these fellows. Now if there is any justice in this world, this must converge, and then there is a natural way of saying that that limit is the value of the integral f. There are many problems that arise. One, will it converge? I do not know whether this converges. Secondly, even if it converges, if one fellow takes one sequence going up to f, another fellow takes another sequence going up to f, the two will give two different limits. What can I do? Which one is the integral? All this is sorted out by one fundamental theorem called the monotone convergence theorem, which says that such problems will not arise. Integral f1 will converge and it will be independent of the sequence chosen to converge to f. Okay. So that's what the most fundamental theorem in one of the first fundamental theorems in defining the integral. Then monotone convergence theorem. The monotonicity is because these are non-decreasing functions. Monotone convergence theorem assures that 1 integral fn d mu over omega limit n tending to infinity exists. 2 if fn increases to f, gn also increases to f, then limit n tending to infinity integral fn d mu is equal to limit n tending to infinity integral gn d mu. So, whichever sequence you choose to approximate f, they are going to give you the same. That limit is something which depends only on f, and that number is called the integral of f. We can therefore define integral f d mu over omega to be limit n tending to infinity omega fn d mu, where fn can be any such sequence, Okay. So, any such sequence you can choose, approximate, and we will see some example where we do that precisely, where fn is any such sequence and it goes to that. Okay. So, what have we achieved? First step, we generalized step functions and got the meaning of the integral of simple functions. Second step, we got the meaning of integral of non-negative measurable functions. So, we defined the integral of non-negative measurable functions. So, real, all so far we are only real valued. Next we will look at general real valued functions, need not be non-negative. Okay. So, the step 3 is f is f mapping omega to r, measurable function again. That is the mu of the set of all omega in omega such that f omega is less than or equal to x is defined for all x. That is, the cumulative distribution function is well defined, if you can call it cumulative distribution function. Okay. Now, how do I handle such functions? Now, it is very common sense again. If you think of integral as area, whenever we have a curve going up and down, to calculate the total area, we calculate the area which is above the x axis, we calculate the area which is below the x axis and subtract. That gives me the total integral. So, the area above the x axis and the area below the x axis, take the difference, you get the actual integral. But when you take the difference, if one of them becomes infinite, no problem. If both of them become infinite, I will have infinity minus infinity, which is not defined. So, that is all that is being done here also. Okay. So, suppose I have such a function. Now, first we look at the area f of x equal to f of x if f of x is positive and 0 if f of x is negative. So, what I am doing is I am completely filtering out all that information below the x axis, and I am looking only the signal above the x axis. And similarly, I define f of minus x to be minus f of x if f of x is negative and 0 if f of x is positive. Now, what am I doing here? I am now switching off the signal which is on top and looking at the signal which is at the bottom and flip it up, make the negative to positive by taking that, flipping that curve above the x axis. So, first I erased all the signal which was above the x axis and the signal which was below the x axis I just made it positive, took the negative of that, so that both these functions are now non-negative measurable function. They both will be non-negative and that turn out to be measurable function. If they are non-negative measurable function, previous step tells us how we can define integral of both these, and if one of them is finite, then we can take the difference as the integral. Okay. So by step 2, we can define integral f plus d mu over omega and integral f minus d mu over omega. Well, when I said above it convert, it could convert to plus infinity also, that is allowed. Okay. Okay. Then if either integral f plus d mu is finite or integral f minus d mu is finite, we define, or both, we define integral f d mu over omega to be integral f plus d mu minus integral f minus d mu, and that is how we define integral with respect to a measure. Okay. Simple common sense. There are technical details in justifying this common sense, but basically the idea is simple common sense. First you learn how to handle positive, then you learn how to handle loss and make sure that both of them do not become infinite, then you can really do it. Okay. So first simple functions, non-negative simple functions, then non-negative functions, then general functions. General functions are split into two non-negative functions, and non-negative functions are split into limits of simple functions. So therefore it is enough if you define the integral of simple function, the flow goes on and you can generate the integral of a general function. This is the general idea of integral with respect to a measure. Okay. Any questions? Okay. I'm sure this is some of the things, if you had attended Atreya's lecture, he would have done it. Okay. So the monotone convergence theorem is a very important theorem. It allows you to go through these limiting processes. And of course I have done only for real. How do I do for complex? Real part plus I times the imaginary part. So suppose the last step is f complex, then f is equal to f1 plus I f2, then integral f is defined as integral f1 plus I times integral f2. This is real, so this can be defined. This is real, therefore that can be defined, and therefore everything is done. Okay. So that's not a problem. So you have to actually go backwards and see. Well, I know how to define complex if I know how to define real. I know how to define real if I know how to define non-negative. I know how to define non-negative if I know how to define simple, and I know how to define simple. That's what the whole idea of integration over a measure is. Okay. Okay. Shall I erase all this? Now let us take the special case. The mu is counting measure. And do a few things. So let us look at the special case where we are using the measure to be the counting measure. For finite set, the measure is the number of points in that set, and for infinite set, the measure is the infinity, plus infinity. Okay. Now suppose I have such a measure first case, suppose omega is a finite set. The whole sample space itself is finite, say in the measure in probabilistic language. So I have the whole world itself is a finite set, in which case define omega to be, it will be something like this, omega n. Omega will have n points. Now if I have n points, suppose you have any function f omega to c, suppose I have a complex valued function defined on this set omega, then there will be n values, f of omega 1, f of omega 2, f of omega n. We can form a vector whose components are these n. So we can form a vector from f as, I will call that corresponding vector as capital F. This little f I will call it as capital F. It is this vector f of omega 1, f of omega 2, f of omega n. And therefore, functions over such sets are, I will forget about the measure, the functions over such sets are nothing but vectors, and since these components are all complex, namely the values of the function, therefore this is a vector in the n dimensional complex space. So now what is meant by integral in this now? What will be integral of f d mu over omega? Every function is a simple function because it takes constant values on a singleton set, which is a measurable set. So we can think of this function as a1 chi of omega 1 or f omega 1 chi of omega 1, f of omega 2 chi of omega 2, and so on, f of omega n chi of omega n, right. The characteristic function of the singleton set has one value there and 0 elsewhere. So if you look at this function, this fellow is 1 only at omega 1, and therefore totally it becomes f of omega 1 at 1, all the others are 0. If you want to look at the value at omega 2, all these will switch off and this will give you f of omega 2, and so on and so forth. So the function can be written like this, and it's a finite thing, and therefore it will be the integral of all these fellows. But now the integral of all these fellows is f of omega 1, measure of omega 1, which is 1. Measure of omega 1 is the number of points in that singleton set, which is 1. So it is f of omega 1 mu of omega 1 plus etc. f of omega n mu of omega n, and therefore it is simply summation j equal to 1 to n f of omega j. The integral is simply the sum. Okay, that is the generalization. Integral is essentially the generalization of the idea of the sum of a finite number of L. Okay, now suppose I want to look at the L2 functions on this. What does that mean? It is the set of all functions from omega to c such that integral mod f omega squared d mu mod f squared d mu is less than infinity, right. That is the definition of the L2 functions. Now what does this mean? All those functions, the integral now is simply summation j equal to 1 to n mod of f omega j square. That is definitely finite. because we are adding only a finite number of quantities. So therefore this is the set of all functions f mapping omega to C with norm of f in this measure to be equal to sum of mod of f omega j squared, j equal to 1 to n square root. This integral, which is the standard Euclidean norm for the corresponding vector. Okay, this is nothing but the norm of f, the L2 norm of f, 2 norm of f, the corresponding vector. Okay, so basically, what does this mean? Looking at the L2 space of functions from a finite set to C with respect to the counting measure boils down to looking at the Euclidean space with n components. So therefore L2 omega mu in this case is completely identified with the little L2 with n components with complex coefficient. That is simply the case. So there is nothing great about it, but this is a good identification that, oh, that's what's happening. It's all L2 spaces with some counting measure. That's what is going to come out. Eventually, we will see all Hilbert spaces are simply this. Okay. Now the next case I will do is, suppose omega is an infinite sequence, that is a countable set, that is omega is equal to omega 1, omega 2, omega n, etc. It is a sequence. Now I am going to look at an infinite sequence with counting measure. The sample space is a discrete space, but it is an infinite discrete space, and now I am going to look at the counting measure on this, and then I want to look at L2 omega mu. What is your guess? What is going to happen? It is simply L2, number of components is going to go to infinity. So we are going to say this is identified with L2C, that is infinite number of components whose sum square is finite. Take all those, which is the set of all f such that summation j equal to 1 to n mod f omega infinity mod f omega j squared is finite. So again nothing new, but only thing is we are now identifying our old space in the language of measures. It is simply the L2 space of all those functions which are square integrable with respect to the counting measure and defined on a countably infinite set. That is how we are identifying. Is that okay? The third situation is what we are going to discuss, which is new. We are now going to make omega an uncountable set. What will happen? Okay. The case 3 is the non-trivial case which we will look at. Omega an uncountable set, an uncountably infinite set. Now for example, we can take omega to be the interval 0 to 1, right, but now we are not putting the Lebesgue measure on that, we are putting the counting measure on that. So we are looking at, for example, we can think of the interval 0 1, its measure is not 1, the length, it is infinity now, because we are using the counting measure. So same set, but we can use different measures. That is what we do in the real line. We use different measure. Each cumulative distribution function gives a measure on the real line, okay, called the Steele-G measure in the probability theory. This is exactly what we do. Okay, infinite set with, again recall, counting measure. See, this omega need not even be a part of the real line. I am just trying to tell you that it could possibly, you can think of omega as the interval 0, 1, which are uncountable set, but I am not using the length measure there, I am using the counting measure there. So, now let us do, this is what I wanted to start with, this is what I wanted to assume and go to these definitions, but suddenly it occurred to me maybe I should review this. Okay. Now let us look at this space little bit carefully. And I am interested in L2 only. So, okay, suppose I have f of omega to c, okay, and say f is non-negative. Remember our definition of the integrals were first simple functions. What is meant by simple functions? Those which take constant values on measurable sets, and measurable sets are anything. So, we can take measurable sets to be singletons. So, we will come back to either that case or this case. So, the first case, if any simple function is taking values on a finite set and otherwise it is 0. So, it is very easy to define the integral again as before, but now what happens when we go further? So, suppose f is greater than or equal to 0. So, our main point will be what will happen for non-negative functions, because the moment I know non-negative functions, I know general functions. I will split it into two non-negative functions. So, main step is how do I do non-negative functions. Now, suppose f is not 0 only on a finite set, then there is no problem. Suppose f is not 0 only on a finite set. What does that mean? Say omega 1, omega 2, omega k. Then f is simply f of omega 1 into chi omega 1 plus etc. f of omega k into chi omega k. All other places it is 0, but that is a simple function now, and therefore we know how to integrate. Simple, non-negative, therefore we are done. We know how to do it. We know how to integrate non-negative simple functions. Now, suppose f is not 0 at a sequence of points, again the same story. Let us even do that, okay, to illustrate that. To illustrate my monotone convergence theorem, I will again do it. Suppose f is not equal to 0 in an infinite sequence of points, only in an infinite sequence of points. Say omega 1, omega 2, omega n, etc. Okay. So, first I saw if I had a non-negative real valued function which vanished only at which is non-zero only at a finite number of points, it simply means it is a simple function, non-negative, I can integrate. Then I said suppose f is not 0, but it is not 0 in an infinite number of points, but that infinite number of points is a sequence of points, countably infinite number of points. In that case, I am going to actually do monotone convergence theorem. Let us look at fn to be the function which takes the same values as f at these points and then switches off. Okay. So, Fn define omega to c, define Fn omega to c as Fn of omega is equal to f omega for omega equal to omega 1 up to omega 1, 0 otherwise. Right? What type of function Fn is? It is a simple function because it takes non-zero values only in a finite number of points, and therefore back it is like a function like this. It is a function like this. Fn is not 0 only at a finite number of points. So, by case A, integral Fn d mu is equal to summation f omega j, j equal to 1 to n, 1 to n, because the integral is simply taking the values, the integral f is simply summation j equal to 1 to n. Look at the profit from each one of these banks and you get the total value of the integral. Okay. So, no problem there also. So, Fn's are simple, non-negative. So, Fn non-negative simple functions. Now, what happens as n goes to infinity? F1 will pick up the value here, F2 will pick up the value there also, F3 will pick up the value at F3 also. As n goes on increasing, we will pick up all the values of f. So, Fn tends to f. And is Fn increasing? Yes. F1 and F2 agree here, but F2 is 1 here, but F1 is 0 there. So, therefore, as we go along, we pick up more and more points non-zero values, and therefore, it is non-decreasing. So, actually Fn increases to f. So, Fn non-negative simple functions increasing to f. What does monotone convergence theorem say? Their integral must converge to integral f. Therefore, by MCT, integral Fn d mu converges to integral f d mu. But what is so what is this? This is j equal to 1 to n f omega j, that converges to integral f d mu. That means integral f d mu is equal to summation j equal to 1 to infinity f omega. Again add all the values, that is all. Again it is generalization of the sum. But now that value can be infinite, because we do not know whether that series converges. If that series converges, it has a finite integral. If that series diverges, it has an infinite integral. Because it is positive terms, these are all non-negative terms, this thing is going, the partial sums are going on increasing, either they will be bounded above and converge to a finite value, or keep flying off to plus infinity. So, that value can be either finite or plus infinity. In either case, if it is plus infinity, we define the integral to be plus infinity. If it is finite, we define the integral to be that finite value. So, therefore, there is no problem about f being not equal to 0 in an infinite sequence. So, what did we start with? We started an uncountably infinite set and we looked at a non-negative function, and we said that if it is not 0 only at a finite number of points, no problem, I can define the integral. If it is not 0, even if it is only at an infinite sequence of points, no problem, I define the integral. In both the cases, the integral is simply the sum of all the values. Okay, just add up all your profits, total profit. Right. Now comes the difficult case. What is the difficult case? We want to have an uncountable number of points. If the function is not 0 at an uncountable number of points, what do I do? Okay. So, therefore, what I will do is, I am not interested in this, I am not going to go into the details. I am now going to look at suppose, let me see what I will do. Again I am having mu to be an uncountable set. Okay. Suppose I have a function f which is in L2, what does that mean? That implies integral of mod f squared d mu is finite. Suppose I have a function, I want to know what is the space look like. So, I take a function in that space and see what is the structure of that function, right. Take any finite, you will see what is going on. Finally, we will see what is going on. I hope I will have the time. Okay, take any finite subset, omega 1, omega n of omega. So, here is my omega, I am just picking up randomly n points. Take any n points. And then define some new function, let us say g of omega is equal to mod f omega squared if omega equal to omega j 1 less than equal to j less than equal to n, 0 otherwise. Okay, so what am I doing? At this point, I am taking the value mod f omega 1 squared for omega. At this point, I am going to take mod f n 1 squared, but all other points I am going to take it to be 0. Now, compare this function and what is the difference between the two functions? What is, they both coincide at these points, but at other points this fellow is 0, there is a chance that that fellow is not 0 and may be positive, therefore positive. So, therefore, at these points both match and at other point g is 0, f can be positive. So, we can say that this is always true by construction. With the construction of this function, this is true, and therefore, the all are non-negative. No, this is non-negative, this is non-negative. If I have two graphs, if one graph lies below the other graph, the area of this lower graph must be smaller than the area of the, this is the monotonicity of the integral. G d mu will be less than or equal to integral mod f omega squared d mu. Okay, that clear? Now, what are we given? We are given that this is finite, so that is some number alpha. So, let us call it as alpha, which is finite. By our hypothesis, f is in L2 omega and therefore it is less than alpha. So, what have we finally achieved so far? What we have achieved is, okay, what is this integral now? That is non-negative function taking non-zero values only at a finite number of points. So it is a simple function. Its integral is simply add the values. So it is just mod omega j squared, j equal to 1 to n. That's all. So that is less than or equal to this. So let me make a conclusion. Okay. F belongs to L to omega mu. This observation, final observation that I am going to make out of this is the most important thing. This implies for any finite subset omega 1, omega 2, omega n in omega, summation j equal to 1 to n mod omega j squared is less than or equal to alpha less than infinity, where alpha is that integral mod f squared. This is the conclusion. Okay. So one possible thing we have found is the following, that is, if we now, what is the conclusion we have got? I have this omega, randomly pick any points and take the value at these points to be the square value of the function, then the total payoff cannot be more than alpha at these points. All these banks put together, at each bank the interest is mod f omega j squared, and if you take randomly n banks, the total interest you get cannot be more than from these banks cannot be more than the complete interest that you got. This is common sense. Okay. This is the interest obtained from only these banks. The integral is the interest obtained from the entire bank, taking mod omega j squared as the interest. Okay. Now what sort of conclusion can we draw? Remember, now everything is real. These are all real. These are all non-negative. Alpha is real, alpha is non-negative. We are dealing only with non-negative real numbers. What I say is, I have a bag full of, at each point if I take mod f omega squared, I have a bag full of non-negative real numbers. Randomly pick n coins from that bag. The total value cannot be greater than the total value of the bag. Common sense. Okay. All we have done is that we have a bag full of coins. The coin values are mod f omega squared, and the number of coins is uncountable. From that, if you pick a finite number of coins, the total money you got is less than or equal to the total money in the bank. That common sense thing has been expressed in the mathematical language for integrals in this format. That's all. Right. So if that is the case, suppose I pick 100 coins, certain number of coins, okay, from this bag, this omega bag. I now pick number of coins. The coin values are mod f omega squared. Okay, if I pick up coin from a point I pick, and the coin value is mod f omega squared at that point. Suppose I now pick randomly n coins, and I observe that each coin that I picked has value more than 2 rupees. Right? I have a bag full of coins. I randomly pick n coins, and I observe that each coin value is more than 2 rupees. Therefore, the value of the coins I picked must be at least, suppose I pick n coins and I observe that each coin the value is at least 2 rupees, then the n coins value must be at least 2n rupees. So, the value, let me put it this as value of n coins, each at least, or each at least 2 means each greater than 2 rupees, then total will be greater than or equal to 2n, right. However, the value cannot be more than the value in the bank, in the bag. The total value in the bag is alpha. So, what does that tell about n? N must be less than or equal to alpha by 2. So, if you go on picking up too many coins, then at least one of the coins will fall below the value of 2 rupees, because the number of coins that you can pick having value at least 2 rupees cannot exceed alpha by 2. This is a common sense. I have a bag full of coins. The total value of the bag is alpha rupees, and I pick n coins, and I observe that each coin is at least 2 rupee value. So, therefore, total value is 2n, at least 2n, but the total value is at most alpha. Therefore, n must be less than or equal to alpha by 2. Now, I can replace this 2 by some epsilon, then this will become alpha by epsilon. So, what I want to make conclusion here is that the number of points in omega at which mod f omega squared can be greater than epsilon squared can be at most alpha by epsilon squared for any epsilon positive. I replace 2 rupees by epsilon squared rupees, that is all, something positive. For any value, the total number of coins which you can pick whose value is at least that epsilon cannot be more than alpha by 2. What does that mean? This n has to be finite, because this is finite, this is finite, therefore, at most a finite number, n is an integer, so it cannot exceed some real number. There are only a finite number of positive integers from here to here. So, therefore, conclusion, the set of all omega in omega such that mod of f of omega is greater than epsilon is a finite set for every epsilon greater than 0. Very complicated, but statements from very simple ideas. I have a bag, I am picking up coins, I am looking at the values. So, what is the conclusion? If I had an uncountably infinite set, and if I had a function which is in L2 of that, then the number of points that where it can exceed epsilon in modulus can be at most finite, can be only finite. Now, from this we can conclude that the number of points where it can be non-zero is to be either finite or an infinite sequence. The function cannot be non-zero at too many points. It has to be non-zero only at a finite number of points or countably infinite number of points. So, let me just do that, and this is a standard trick in analysis. So, you will notice this. So, I can write the set of all points where f omega is not 0 is the same as the set of all points where mod f omega is not 0 . Now, if mod f omega is not 0, it has to be greater than some 1 by n, and therefore, you write it over all n. You can write it like this, because if anything here is there, anything there is here. If you take any point here, it is greater than 1 over n, therefore, it is greater than 0. If you take any point greater than 0, it has to be greater than 1 over n for some n, therefore it is here. So, it is in both these two are equal sets. Now, what do I know about these fellows? If I take this as epsilon, I have this situation, it has to be finite. So, each one of this is finite. So, I have a countable union of finite sets. So, this is equal to finite or a infinite sequence. So, that is what I will conclude today's lecture with this. I have still not finished with the L2 omega, but almost there. So, conclusion, this is the most important conclusion. The same idea I will use again at least 2 or 3 more times. Omega uncountable set, this was the last case, okay. Finite and infinite we have finished. F belongs to L2 omega mu. Mu is counting measure. Implies the set of all omega where f omega is not equal to 0 is either finite or countably infinite. And in that case, if we call S, I will call this set as the support of f. The support of f is the place where omega f does not vanish. Then integral omega mod f omega squared d mu is simply summation over all the points in the support, you take the value. This again the summation generalization. Okay. So, only points, only some banks give 0, some banks give positive interest. So, if you want to calculate the total interest, you have to add all the positive interest. I know how to add finite number, I know how to add infinite sequence of numbers positive, and only those 2 cases are possible. You do not worry about other cases, it will not happen. Okay. So, if what this says, if we have total interest is finite, then it must happen that only a finite number of banks have given you positive interest, or an infinite sequence of banks have given you positive interest, all other banks should have given you 0 interest, that is all. That is the common simple sense, that f belongs to L2 omega with respect to the counting measure simply means that f can vanish, f can be non-zero either in a finite set or a countably infinite set. That is the moral of the story, which is simple common sense, okay. But it requires all these arguments to get it mathematically valid for this setup, okay. Now, therefore, what it says is L2 functions really mean like our old either finite number of points like L2n or an infinite sequence of points like L2. But the only problem when you come is this infinite number of points will change with different functions. One function may have a certain countable sequence of points where it is not 0, another function will have another set of points where it is not 0, and therefore it is a very complicated L2, not the L2 of z or L2 of n, okay, over the only the components, the integer, the components have to be indexed over omega. If you want to identify this as a vector, it will no longer be a sequence of vectors, the components have to be indexed over omega, but then when you index, only a countable number of them will light up, all others will be 0. Either a finite number of them will light up or a countably infinite number of them will light up. That is what the L2 space over counting measure is. Okay. I will continue from here in the next class. Next is Monday 3 to 4.